In statistics, the number of degrees of freedom is the number of values in the final calculation of a statistic that are free to vary. The number of independent ways by which a dynamic system can move, without violating any constraint imposed on it, is called number of degrees of freedom. In other words, the number of degrees of freedom can be defined as the minimum number of independent coordinates that can specify the position of the system completely. Estimates of statistical parameters can be based upon different amounts of information or data. The number of independent pieces of information that go into the estimate of a parameter are called the degrees of freedom. In general, the degrees of freedom of an estimate of a parameter are equal to the number of independent scores that go into the estimate minus the number of parameters used as intermediate steps in the estimation of the parameter itself. Mathematically, degrees of freedom is the number of dimensions of the domain of a random vector, or essentially the number of free components. The term is most often used in the context of linear models, where certain random vectors are constrained to lie in linear subspaces, and the number of degrees of freedom is the dimension of the subspace. The degrees of freedom are also commonly associated with the squared lengths of such vectors, and the parameters of chi-squared and other distributions that arise in associated statistical testing problems. While introductory textbooks may introduce degrees of freedom as distribution parameters or through hypothesis testing, it is the underlying geometry that defines degrees of freedom, and is critical to a proper understanding of the concept. Walker has stated this succinctly as the number of observations minus the number of necessary relations among these observations. Conceptual history. Although the basic concept of degrees of freedom was recognized as early as 1821, in the work of astronomer and mathematician Carl Friedrich Gauss, its modern definition and usage was first elaborated by English statistician William Seeley Gosset. In his 1908 Biometrica article, The Probable Error of a Mean, published under the pen name Student. While Gosset did not actually use the term degrees of freedom, he explained the concept in the course of developing what became known as student's t-distribution. The term itself was popularized by English statistician and biologist Ronald Fisher, beginning with his 1922 work on chi-squares. Notation. In equations, the typical symbol for degrees of freedom is nu. In text and tables, the abbreviation df is commonly used. R.A. Fisher used n to symbolize degrees of freedom, but modern usage typically reserves n for sample size. Residuals. More concretely, the number of degrees of freedom is the number of independent observations in a sample of data that are available to estimate a parameter of the population from which that sample is drawn. For example, if we have two observations, when calculating the mean we have two independent observations. However, when calculating the variance, we have only one independent observation, since the two observations are equally distant from the mean. In fitting statistical models to data, the vectors of residuals are constrained to lie in a space of smaller dimension than the number of components in the vector. That smaller dimension is the number of degrees of freedom for error. Example. Perhaps the simplest example is this. Suppose the random variables each with expected value mu, and let be the sample mean, then the quantities are residuals that may be considered estimates of the error as xi minus mu. The sum of the residuals is necessarily zero. If one knows the values of any n-1 of the residuals, one can thus find the last one. That means they're constrained to lie in a space of dimension n-1. One says that there are n-1 degrees of freedom for errors. An example which is only slightly less simple is that of least squares estimation of A and B in the model where xi is given, but A and hence y are random. Let M be the least squares estimates of A and B. Then the residuals are constrained to lie within the space defined by the two equations. One says that there are n-2 degrees of freedom for error. Note about notation. The capital letter Y is used in specifying the model, while lowercase y in the definition of the residuals. That is because the former are hypothesized random variables and the latter are actual data. We can generalize this to multiple regression involving p-parameters and covariates, in which case the cost in degrees of freedom of the fit is p, degrees of freedom of a random vector. Geometrically, the degrees of freedom can be interpreted as the dimension of certain vector subspaces. As a starting point, suppose that we have a sample of n independent normally distributed observations. This can be represented as an n-dimensional random vector. Since this random vector can lie anywhere in n-dimensional space, it has n degrees of freedom. Now, let be the sample mean. The random vector can be decomposed as the sum of the sample mean plus a vector of residuals. The first vector on the right-hand side is constrained to be a multiple of the vector of 1, s, and the only free quantity is. It therefore has 1 degree of freedom. The second vector is constrained by the relation. The first n-1 components of this vector can be anything. However, once you know the first n-1 components, the constraint tells you the value of the nth component. Therefore, this vector has n-1 degrees of freedom. Mathematically, the first vector is the orthogonal, or least squares projection of the data vector onto the subspace spanned by the vector of 1, s. The 1 degree of freedom is the dimension of this subspace. The second residual vector is the least squares projection onto the dimensional orthogonal complement of this subspace, and has n-1 degrees of freedom. In statistical testing applications, often one isn't directly interested in the component vectors, but rather in their squared lengths. In the example above, the residual sum of squares is if the data points are normally distributed with mean 0 and variance. Then the residual sum of squares has a scaled chi-squared distribution, with n-1 degrees of freedom. The degrees of freedom, here a parameter of the distribution, can still be interpreted as the dimension of an underlying vector subspace. Likewise, the one-sample t-test statistic follows a student's t-distribution with n-1 degrees of freedom when the hypothesized mean is correct. Again, the degrees of freedom arises from the residual vector in the denominator. Degrees of freedom in linear models. The demonstration of the t and chi-squared distributions for one-sample problems above is the simplest example where degrees of freedom arise. However, similar geometry and vector decompositions underlie much of the theory of linear models, including linear regression and analysis of variance. An explicit example based on comparison of three means is presented here. The geometry of linear models is discussed in more complete detail by Christensen. Suppose independent observations are made for three populations, and the restrictions of three groups and equal sample sizes simplifies notation, but the ideas are easily generalized. The observations can be decomposed as where are the means of the individual samples, and is the mean of all three n observations. In vector notation, this decomposition can be written as the observation vector, on the left-hand side, has 3n degrees of freedom. On the right-hand side, the first vector has 1 degree of freedom for the overall mean. The second vector depends on three random variables, and however, these must sum to 0 and so are constrained. The vector therefore must lie in a two-dimensional subspace, and has 2 degrees of freedom. The remaining 3n-3 degrees of freedom are in the residual vector, sum of squares and degrees of freedom. In statistical testing problems, one usually isn't interested in the component vectors themselves, but rather in their squared lengths, or sum of squares. The degrees of freedom associated with a sum of squares is the degrees of freedom of the corresponding component vectors. The three-population example above is an example of one-way analysis of variance. The model, or treatment, sum of squares is the squared length of the second vector, with 2 degrees of freedom. The residual, or error, sum of squares is with 3 degrees of freedom. Of course, introductory books on ANOVA usually state formulae without showing the vectors. But it is this underlying geometry that gives rise to SS formulae, and shows how to unambiguously determine the degrees of freedom in any given situation. And the null hypothesis of no difference between population means the sums of squares have scaled chi-squared distributions, with the corresponding degrees of freedom. The F-test statistic is the ratio, after scaling by the degrees of freedom. If there is no difference between population means this ratio follows an F distribution with 2 and 3n-3 degrees of freedom. In some complicated settings, such as unbalanced split plot designs, the sums of squares no longer have scaled chi-squared distributions. Comparison of sum of squares with degrees of freedom is no longer meaningful, and software may report certain fractional degrees of freedom. In these cases, such numbers have no genuine degrees of freedom interpretation, but are simply providing an approximate chi-squared distribution for the corresponding sum of squares. The details of such approximations are beyond the scope of this page. Degrees of freedom parameters in probability distributions. Several commonly encountered statistical distributions have parameters that are commonly referred to as degrees of freedom. This terminology simply reflects that in many applications where these distributions occur, the parameter corresponds to the degrees of freedom of an underlying random vector, as in the preceding ANOVA example. Another simple example is, if are independent normal random variables, the statistic follows a chi-squared distribution with n-1 degrees of freedom. Here, the degrees of freedom arises from the residual sum of squares in the numerator, and in turn the n-1 degrees of freedom of the underlying residual vector. In the application of these distributions to linear models, the degrees of freedom parameters can take only integer values. The underlying families of distributions allow fractional values for the degrees of freedom parameters, which can arise in more sophisticated uses. One set of examples is problems where chi-squared approximations based on effective degrees of freedom are used. In other applications, such as modeling heavy-tailed data, a T or F distribution may be used as an empirical model. In these cases, there is no particular degrees of freedom interpretation to the distribution parameters, even though the terminology may continue to be used. Effective degrees of freedom. Many non-standard regression methods, including ridge regression, linear smoothers, smoothing splines, and semi-parametric regression, are not based on ordinary least squares projections, but rather on regularized least squares. And so degrees of freedom defined in terms of dimensionality is generally not useful for these procedures. However, these procedures are still linear in the observations, and the fitted values of the regression can be expressed in the form whereas the vector of fitted values at each of the original covariate values from the fitted model. Y is the original vector of responses, and H is the hat matrix or, more generally, smoother matrix. For statistical inference, sums of squares can still be formed. The model sum of squares is, the residual sum of squares is. However, because H does not correspond to an ordinary least squares fit, these sums of squares no longer have chi-squared distributions, and dimensionally defined degrees of freedom are not useful. The effective degrees of freedom of the fit can be defined in various ways to implement goodness of fit tests, cross-validation, and other statistical inference procedures. Here one can distinguish between regression effective degrees of freedom and residual effective degrees of freedom. Regression effective degrees of freedom. Regarding the former, appropriate definitions can include the trace of the hat matrix, TR, the trace of the quadratic form of the hat matrix, TR, the form TR, or the Satterthwaite approximation, TR2, TR. In the case of linear regression, the hat matrix H is x minus 1x, and all these definitions reduce to the usual degrees of freedom. Notice that the regression degrees of freedom in linear models are the sum of the sensitivities of the fitted values with respect to the observed response values, i.e., the sum of leverage scores. Residual effective degrees of freedom. There are corresponding definitions of residual effective degrees of freedom, with h replaced by I minus h. For example, if the goal is to estimate error variance, the REDF would be defined as TR, and the unbiased estimate is, or. The last approximation above reduces the computational cost from O to only O. In general, the numerator would be the objective function being minimized, e.g., if the hat matrix includes an observation covariance matrix, sigma then becomes general. Note that unlike in the original case, non-integer degrees of freedom are allowed, though the value must usually still be constrained between 0 and n. Consider, as an example, the k-nearest neighbor smoother, which is the average of the k-nearest measured values to the given point. Then, at each of the n measured points, the weight of the original value on the linear combination that makes up the predicted value is just 1, k. Thus, the trace of the hat matrix is n, k. Thus, the smooth cos n, k effective degrees of freedom. As another example, consider the existence of nearly duplicated observations. Naive application of classical formula n-p would lead to overestimation of the residual's degree of freedom, as if each observation were independent. More realistically, though, the hat matrix H equals x minus 1x, sigma minus 1 would involve an observation covariance matrix sigma indicating the non-zero correlation among observations. The more general formulation of effective degree of freedom would result in a more realistic estimate for, e.g., the error variance sigma 2, which in its turn scales the unknown parameters a posteriori standard deviation. The degree of freedom will also affect the expansion factor necessary to produce an error ellipse for a given confidence level. Other formulations. Similar concepts are the equivalent degrees of freedom in nonparametric regression, the degree of freedom of signal in atmospheric studies, and the non-integer degree of freedom in geodesy. Alternative, the residual sum of squares has a generalized chi-squared distribution, and the theory associated with this distribution provides an alternative route to the answers provided above.